afternoon, everyone. First and foremost, I would like to thank the seminar organizer for this invitation, as well as the presence of all of you here today. My name is Rodrigo Ferreira, and today I'll be speaking on the manufacturing and characterization of a piezoresistive strain sensor based on the Argo PDMS Composite for Skin and Prosthetic Systems, a work developed here at C-MAST with the support of my scientific advisors, Abílio Silva and João Nunes Pereira. In this presentation, I will start by giving the context, motivation, and objectives for this work, followed by a shift towards the materials and methods, the employed characterization techniques, the developed proofs of concept, and ending with the joint conclusions and some future works. Starting with the context, we should first consider the influences that led to this work, such as the great variety of composite materials employed in sensorial applications, whose greatest advantages are their high potential, versatility, and influence on the final performance of the sensors they integrate. In addition, piezoresistive sensors are particularly useful in this type of application due to their simplicity, sensitivity, and stability, which is exacerbated with the use of carbon-based materials, such as graphene, due to their excellent electromechanical capabilities, high specific surface area, and non-behavior. Thus, when considering a new generation of sensors, developments must involve greater sensitivity, linearity, and durability through simpler, cheaper, and more environmentally friendly methods. This brings us to our main motivations, which consist of more personalized, efficient, and comfortable wearable devices to rehabilitate patients, and these must leverage our growing concern for personal health, as well as the explosive growth of this technology. Abandoning some of the more traditional methods that are still used in many healthcare infrastructures today would also prove advantageous in favor of new approaches that focus more on the individual level. With this in mind, we set out to develop a piezoresistive strain sensor based on the Argo PDMS Composite, with the aim of understanding the operating mechanisms and interactions that occur inside a composite, as well as detecting and monitoring user movements and actions. Some other objectives included delving into the principles of material and manufacturing process selection, observing the electromechanical performance depending on the filler's concentration, as well as to conduct a small study on the conformity, prolonged use, and user acceptance. Starting with the materials, the chosen filler was reduced graphene oxide, also known as Argo, which are microparticles more affordable than pure graphene that retain similar electromechanical capabilities. The chosen matrix was PDMS, a high-performance silicone very popular in this type of application, usually made up of an elastomer plus crosslinker kit. Due to the nature of the manufacturing process, various dispersants were tested, such as 1,4-dioxane and distilled water, but today we will be focusing on the one that gave us the best results, isopropyl alcohol. Similarly, despite multiple elastomer crosslinker ratios being tested, only the 15:1 ratio will be considered today, and especially the 120/15 configuration, since this was the best alternative of all, and the one we used to produce our composites. Unlike pristine PDMS production, where only the mixture between the elastomer and the crosslinker was cured, the approach for manufacturing the composite was a little bit more complex and time-consuming, where we decided to integrate elements of both solvent casting and solution casting, followed by a cure at 120 degrees for 20 minutes. At the end of this process, which may take up to 4.5 hours, we obtained a ready-to-use composite, which was very different from pure PDMS, as we can see from figure 1. Of all the produced samples, only the ones with an Argo content of 3, 4, and 5% showed us measurable electrical activity, and thus were the only ones used in the characterization techniques. The main objectives during this phase were to obtain a film configuration with the physical and electromechanical capabilities needed to detect joint movements and breathing patterns, while maintaining a Young's modulus as similar to the skin as possible. Moreover, discovering the approximate concentration of Argo that would lead to the percolation threshold was also useful, since we wanted to create an efficient electrical conduction network inside our material. Now, starting with the characterization techniques, we began by observing the sample's morphology by SEM, where, unlike pristine PDMS, which had a smooth surface without pores or damage, the surface of the composites had a much more crumpled, wrinkled, and flaky-like appearance, all due to the presence of argon. In addition, while for 3% the filler's dispersion was uniform and well bonded to the matrix, as the argon content increased, the filler's density and the porosity increased as well, along with the glomerates that began to appear in more quantity and size, which of course will affect the mechanical and electrical performance past the saturation point. In the structural characterization by ATR, all characteristic infrared peaks of both PDMS and argon were observed, as you can see in the graph on the left, including the influence their interaction had on the peak's morphology, since the tendency was to lose intensity but gain width due to the loss of purity, but also the creation of new contact points, as you can see on the graph on the right. Regarding the thermal characterization, the TGA test on the left allowed us to conclude that the argon content greatly influenced the thermal stability, where although the degradation temperature was similar for all, at around 400 degrees, the temperature at which the samples lost half their mass and the final residue was much higher for the composites, and especially for the 3% argon sample. On the other hand, the DTA curves on the right allowed us to observe that the degradation was accompanied by endothermic peaks, peaks that could allow us to predict the mass drops in the TGA, while also observing the thermoset-like behavior of this material. In the mechanical characterization, we employed the universal testing machine to carry out tensile tests to both pristine PDMS and the composites, and the 3% argon samples showed stupendous performance when compared to the others, with their average strain and stress values being the closest to our pure PDMS configuration. In addition, a higher argon content was directly related to greater rigidity and brittleness, which was both seen during the manufacturing process and now confirmed by the calculated Young's modulus. We also mechanically tested pure PDMS, where we saw the influence curing temperature had on the final characteristics of the polymer, since the used configuration 120/15 exhibited the most favorable strain and stress values, as well as a Young's modulus very similar to the skins. On the other hand, the other two configurations were cured at lower temperatures and thus showed us less satisfactory characteristics due to lesser promotion of cross-linking and crystal lattice stiffness. Shifting to the electromechanical characterization, the chosen samples were all produced with isopropyl alcohol as a dispersant. The argon content ranged from 3 to 5%, and in total 5 3% samples, 2 4% samples, and 3 5% samples were tested in the following phases. We began with 3-point bending tests using the setup shown in Figure 10, and the first stage consisted of determining the best test speed, where a direct relationship with the gauge factor was observed, since speeds above 4 mm per minute always led to values above 6. However, at very high speeds, the electrical signal acquired by the multimeter was sacrificed due to its low sampling frequency, and so a test speed of 5 mm per minute was chosen. In the cyclic tests, all samples underwent 4 bending cycles at a maximum strain rate between 1.54 and 2.87%, and 3% argon samples showed us a maximum average gauge factor of 14.85, while also exhibiting the most typical electromechanical behavior of all, with excellent linearity and low latency. However, despite the signal having these characteristics, a relative electrical resistance leakage was observed, something common to all tests and which will be discussed later. 4% samples had the highest sensitivity, reaching a maximum average gauge factor of 30.8, an indicator that this may be the concentration within the percolation threshold. Its piezoresistive behavior, however, despite linear with the mechanical strain, the rising peaks denoted the difficulties in returning to the initial state, either due to the viscoelasticity of the material, the hysteresis effect, or a conduction network that may react differently depending on the strain rate. Lastly, 5% samples had the least sensitivity, reached a maximum average gauge factor of 9.16, explained by a more saturated conduction network that may have sacrificed the composite's flexibility. Even so, the acquired signal showed us high linearity and amplitude, although the relative electrical resistance leakage persisted. Therefore, to deepen our knowledge on the conductive network's conformation, the stability and prolonged use, as well as the influence of the viscoelasticity, a sample with 3% Argo was subjected to a 100-cycle stability test. A pronounced conformation period was observed until halfway through the test, where the relative electrical resistance dropped, possibly due to the low strain used. However, from cycle 55 onwards, the signal began to stabilize, which showed us that the material was able to adapt well to the induced mechanical strain. Moreover, we also know that the composite worked perfectly, as the amplitude of its cycles remained more or less the same throughout the entire test. With the bending tests over, we took the best performing samples and tensile tested them using the setup of figure 18, and these showed us that the material structure and the conductive network conformation had a lot of influence, with a pronounced leakage between the first and second cycles, as well as lower strain and sensitivity values. Here, the 3% sample reached a gauge factor of 4.89, followed by the 4% sample at 0.43, and lastly, the 5% sample, where due to its extremely exacerbated response, the gauge factor could not be calculated. The last electromechanical test consisted of tensile straining the samples until the structure lost its interconnections, and a reversible behavior was observed where the samples returned to their normal state when relaxed. In addition, the loss of the electrical component always occurred before the material's structural failure. With the characterization complete, we developed two proofs of concept with the aim of assessing the sensor's performance when used to monitor movements, and the first proof of concept consisted of monitoring the movement of the wrist joint, and by using the setup of figure 22, all flexions and extensions performed by the volunteer were easily captured due to the electrical signal being linear and the piezoresistive behavior very satisfactory, as you can see from figure 21. The second proof of concept consisted of monitoring a user's breathing pattern by using the setup of figure 24, and as you can see from figure 23, the sensor had a worse performance when tensile strained, with heavy filtering having to be applied. However, all 14 inspiration and expiration cycles were able to be captured, a value that we considered healthy for this individual. Taking everything into account, many conclusions could be drawn, including that the crosslinker concentration and curing temperature were the main influences on the mechanical behavior. Generally speaking, samples with 3 and 4% Argo showed us the best properties, which in some cases were very similar to the works developed in the field. Usually, lower strain rates led to higher gauge factors. The addition of filler significantly increased the mechanical rigidity. 3% samples are the best for high strain rate applications, such as monitoring finger movements. 4% samples for intermediate strain rates, such as wrist or chest movements, while 5% samples are more suited for areas with little to no deformation, such as the neck or throat. Lastly, some future works can be developed taking into account what was learned here, including better electrode deposition methods, studying the relationship between the Argo content and its resistivity, exploring new hybrid composites, as well as testing out the performance with new dispersants, new areas of the body, or even developing a sensorial network with these materials. Lastly, I would like to thank C-MAST and UBI's engineering faculty for the assistance to the creation of this work, as well as FCT for all the financial support. Thank you very much.